Can you see the slides?
Yes.
And you can hear it, right? Yeah. Okay. Good. So thanks for inviting me. It's an honor to speak at this conference for Sakai to celebrate the its liberation from admin. It's rather something. So yeah. So I'm going to talk about this topic on relative definability, which is I'm going to be collecting some some things about which many of them have quite easy proofs, and I'm sure they're well known. Also, some of them I actually talked about at the RIMS conference, and they appeared at some proceedings, an article in the RIMS proceedings that actually Sakai was an editor of. So yeah, so let me get started. So the main focus is to quantify the idea that a certain, you have some combinatorial object of size aleph1, and it may be that that having any such object necessarily encodes more information than some other type of combinatorial object. So for example, if you have a ladder system on omega 1, so every C delta is a cofinal subset of delta over type omega, then from that object you can define all kinds of things, a house of gap and the simplified omega 1 Maras, Argentine trees, Kancheman lines, partition of omega 1 to stationary sets, and many other things. And all these claims can be verified just by looking at specific constructions one by one of the relevant objects and see that, yes, indeed, you can define them explicitly from a given lattice system. On the other hand, it not be the case that if you have a partition of omega 1 into stationary sets, then there is a lattice system which you can define from that. Okay, so this is the kind of phenomenon that I want to start looking at. And I'll say that a typical proof of this separation results proceeds in these steps. Well, start with the model V that satisfies some suitable existence pattern of relevant types of objects at some high kappa. And then you pick a sample of those objects. And then you go to some homogeneous extension in which kappa becomes omega 1, and the objects that from the sample have been preserved, and moreover, no objects of unwanted kind are definable from them. Why? Because otherwise they would exist in V by the homogeneity of the forcing, which was not the case for the V you started with. Okay, so that's that's the general scheme of these proofs. And many of these separation results regarding definability, but not all of them can be turned into independence results relative to ZF by going to some natural symmetric submodel of the generic extension you use. Okay, so so let me give a formal definition. So suppose you have two properties, P of X and Q of X, then I'll say that Q of X has definability strength, at least that of P of X, over H omega 2. If there's a formula phi in two variables, like that, whenever you have some A in H omega 2 that satisfies a strong property Q of A, then the set of B in H omega 2 that satisfy this phi with this parameter A satisfies the weaker property P. Okay. Okay, so yeah. So that's a natural definition. Now, of course, this sort of study becomes completely trivial if, let's say, there's a well order of H omega 2 definable without parameters, because then, given any property P, which is realized, just simply look at the first witness in the well order, right? So you don't need any parameters to define some object satisfying the property. So that's not so interesting. So one can, of course, modify this definition in various ways. For example, you could restrict to saying that phi has to be of some bounded complexity, right? So what if this phi that this formula phi that satisfies the simpler object has to be sigma 1 or sigma 0 or something, right? Or you could look at the definability strength over the entire V, not just h omega 2. Or you could just look at definability strength over h omega 2 where you allow real parameters, for example. Okay, so you allow a real parameter in the phi. So for example, let me define this. So given two properties P and Q, then Q of X has definability strength at least out of P of X over h omega 2 with real parameters. If there's a formula phi now in three variables and real R such that whenever you have an A that satisfies a strong property, then if you collect the things in h omega 2 that satisfy phi with A and this real as parameters, then that satisfies the weak property, right? Okay. So again, give an example of things that happen when you look at this notion of definability strength. If you look at the Pmax axiom star, that implies that if P of X is any property definable over h omega 2, which is true about something in h omega 2, then if you look at the property X is a subset of omega 1 not constructible from a real, that has definability strength at least that of P of X over h omega 2 with real parameters, right? So the property being a subset of omega 1 not constructible from a real, sits on top of anything else. And the proof is simple because if star holds and A is a subset of omega 1, which is not in L of R for any real R, then you construct modulo, then L of R together with A is entire h omega 2. So in fact, if you take any B in h omega 2, then there's a Pmax condition, which is essentially real, and something in M in the universe of the condition, so that there's a unique correct generic iteration of the condition. So that correct means sending set of positive sets in the final model are really stationary, which sends A to this parameter. It's distinguished set to this parameter capital A, and moreover it sends some B in its universe to our object B. Okay. So yeah, so I mean, so this what this is saying, right, is that on the star you have it exactly like a two intra-definability degrees model of reals, right, which is everything that lives in so every property that's realized but something in L of R, and then all the rest. Okay, another similar result is that still looking at the intra-definability from reals, is that if BMM holds and the non-stationary ideal is saturated, then again, if P of X is any property definable over h omega 2 that is satisfied, witnessed by something in h omega 2, then now the slightly stronger property of being a stationary and co-stationary subset of omega 1 has maximum definability strength, right? So from anything which is stationary and co-stationary, you should be able to define, together with some real, something that has the property P of X. So now the proof is as follows. So suppose that BMM holds and the non-stationary ideal is saturated, and then you take any subset B of omega 1, and then you take any S, which is stationary and co-stationary. Then I can find a real R such that B is actually in L of R together with S. So this is a bit. So this conclusion is a bit stronger than what we had for the star axiom. Now the proof of this uses the fact that under this hypothesis, psi AC holds. I'll see some a bit more, just remind you of what psi C is in a moment. Every club of omega 1 contains a club constructible from a real, and then every ordinal in omega 2, for every ordinal omega 2, there's a real R that thinks that alpha, that ordinal has cardinality, the kappa, where kappa is the omega 1 of V. So combining these three facts in some way, you can prove this thing. By the way, this second theorem is not subsumed by the first one because MM double plus implies star, but BMM and NS is saturated that does not imply star. In fact, Martin's maximum does not imply star. Okay, so let me digress a bit before digress a bit, and I will say something about psi-AC and some related principle. So psi-AC, the principle that the coding principle that I was referring to before, says that the following: that you have any stationary and co-stationary subsets. You have two stationary and co-stationary subsets of omega 1, S and T. Then there's some ordinal alpha in omega 2 such that for every surjection that you have from omega 1 onto alpha, for any such thing, there's a club C such that for every nu in C, nu will be in the first set S, even only if the order type of the pointwise image of nu by pi is in the second set. So this way, you can prove that. So if this holds, then every function from omega 1 into omega 1 is dominated modulo club by the canonical function of some ordinal in omega 2. And also you have a well order of H omega 2 definable this time with any given partition of omega 1 into stationary sets as a parameter. Okay. So this doesn't quite give you the result about BMM and about non-saturated ideal being saturated, because here for psi-AC you have this well order definable from a partition into saturated sets, omega 1, many of them. And you can force this principle starting from an inaccessible limit of measurable cardinals. Now, consider the following version of psi-AC that says, so now this is a psi-AC relativized to, so this is upper screen as omega 2, omega 1. So that's the ordinals of omega 2 of finality omega 1. And it says that if you have stationary sets S and T in this stationary set, and their complement relative to S omega 1 and omega 2 omega 1 are still stationary, then you have the same conclusion one cardinal up, right? So there's some alpha less than omega 3, such that when you look at any surjection from omega 2 pi from omega 2 onto alpha, then for club many nus, you have that if nu has cofinality omega 1, then nu will be in S, even only if the pointwise image under pi, the order type of that is in T. So again, you can show that this should be this super index here. This principle implies that every function from S omega 2 to omega 1 from this set into omega 2 is dominated modulo club by a canonical function of some alpha in omega 3, and that if you have a partition of this set into omega 2 many stationary sets, then you have a well ordered omega 3 definable from this parameter. Right? It's the same argument. Okay, so now the thing I want to mention now is that in current work in progress with Velichkovich, which we're currently writing up, we think we can, starting with the same assumption, an inaccessible limit of measurables, we can actually build a model forcing which would force this principle. Okay, and this construction involves side conditions of virtual models of two types. but it was too early to talk about this. So I'm just mentioning this as something which is very plausible that it's true. Okay, so but from now on, I will focus mostly on the original definition of notion of without parameters of definability strength. Okay, and the first observation I want to make is that the following, so working just in ZF, the following properties are interdefinable over H omega 2. So by this I mean, right, so that if you have any object that has this property, that object will unavoidably encode enough information to define from it, and usually in quite a simple way, some object of the other sort. So and these properties, for example, being a ladder system is essentially the same in this sense as being a simplified omega comma 1 morass, or being a special orange tree with a witness. By a witness, I mean you also have so you have a partition of the orange tree into countably many anti-chains, or being a countryman line with a witness. And again, a witness for a countryman line would be a partition of the square of the line into countably many chains, or being an indestructible gap with a witness. You can also, there's a natural notion of witness here. Okay, so all these things have the same strength. All right, so now it's easy to see that, you know, if you have a ladder system, you can define all these things. There are classical constructions for this. I mean, not all of them are easy, but, you know, this is for example, Tovarchi, which has a book, right, on exploiting ladder, you know, ladder systems. So that gives you the direction that one implies all of these things. And now to see, for example, the converse, let's see that 5 implies 1. So no, actually I wanted to do 4 implies 1. So if you have a countryman line with a witness, then from that you can define a ladder system. So suppose that, you know, take kappa is omega 1 and take a subset of omega 1, which canonically codes some countryman line on omega 1. And this partition of the square of L into chains, countably many chains. So a countryman line is exactly an uncountable linear order such that L cross L can be written as a union of countably many chains in the product order. Now, it's not completely true, but one can prove that. If omega 1 of, so L of this A, of this subset A of omega 1 that encodes the countryman line, correctly computes that kappa is omega 1. And so just in L omega 2 of A, we may pick the least ladder system on kappa in the well order, in the canonical well order. So that gives you this direction, which is a bit of cheating, right? Because you are using this well order, so it's not so sigma 0 definable, but still it accords to the definition. Still you have this definition over H omega 2. Okay. So now that's a completely stupid remark that ladder systems certainly, you know, they are very power, you know, they encode all this information, but they certainly need to not define everything interesting that may exist in H omega 2. For example, you know, you can have a ladder system and weak club guessing fails, but now you add a Cohen reel, and in H omega 2 of the extension, there is a weak club guessing ladder system D, but no such sequence can be definable from the original C, because otherwise D will be in the ground model by homogeneity of coenforcing. So compare this situation with the situation on the star, in which everything which was not in L of R defined a witness for every true definable property. Right? And yes, and then, well, you could run a similar arguments with other more interesting club guessing properties. And want to mention this because I have a question in a moment. So for example, you could look at this interval hitting principle, which says that there's a ladder system C delta, such that for every club C in omega 1, there's some delta such that a tail of the intervals between given defined by C delta then and the next element in C delta, these all have non-empty intersection with C. That's for a tail of n's. And now you can show that there's a CCC homogeneous forcing P, that the point is homogeneous, definable over H omega 2 without parameters, and which forces this guessing principle. Okay, so so that means here's definition. I'll just keep it, but it's not completely trivial, but it's not too not too hard to show. But so I have this question here that you could, which is whether there's a homogeneous forcing definable over H omega 2 without parameters, which forces club guessing. So I don't know the answer to this. Okay, now let me mention some separation results, and eventually I will, I'll draw a broad picture of what this show. So so it's consistent. So we have that ladder systems are very powerful, but it's consistent to have that there's an Orangine tree T and a gap of omega 1 gap in the reals on the eventual dominance, and a partition of omega 1 into omega 1 many stationary sets, such that no ladder system is definable from these objects. Also, if there's an accessible kernel, then you find in some symmetric submodel of a forcing extension, you have the same conclusions, but actually now where you dropped, you replace definability by existence, right? So there's an Orangine tree, there's an omega 1 gap in the reals, and there's a partition of omega 1 into omega 1 many stationary sets, but there is no ladder system on omega 1. So these two results are related. They go in tandem. But also you can show that it's consistent that there's an Orangine tree T, and there's an omega 1 sequence of distinct reals, and there's a partition of omega 1 into omega 1 many stationary sets, but there is no omega 1 gap definable from these objects. And then this is the companion result that if there's an accessible kernel, then in some symmetric submodel of the forcing extension for 3, you would show that there's an Orangine tree, there's an omega 1 sequence of distinct reals, and the partition of omega 1 into omega 1 many stationary sets, but no gap. And finally, you can show that relative to Z of C, that you can have that there's an Orangine tree T, and the partition of omega 1 into omega 1 many stationary sets, but there is no omega 1 sequence of distinct reals definable from these objects. So it's yeah. And again, if you have an accessible kernel, you can turn the definability into existence or non-existence in this result. And the use of an accessible kernel in the even-numbered parts is actually necessary. So these are equiconsistencies. So let me give an example of how you would prove these things. As I said, so the arguments are quite soft for this kind of separations. So okay, so let me start by let me just give the idea for 1 and 2. So 1 is I want to find a model where there's let me go back, where there's an Orangine tree T and there's this gap and there's this partition of omega 1 into many stationary sets, but there is no ladder system definable from them. Okay, so for this, you simply start with a model where you have an orange and tree on omega 2, and you take any partition of omega 2 into omega 2 many stationary sets. And now you consider the CCC forcing. There's a natural CCC forcing that adds an omega 1 gap. Okay, this should be omega 2 gap, sorry, yeah. And then you take a generic for that and then call this FG is the generic gap added. Now, okay, now you use the fact that every CCC forcing will preserve the orange ions of T. So in particular, T remains orange ion in the extension. That's a standard argument. So yes, which I will just skip. So now now what you do is you collapse omega 1 to omega over this extension, and then well there T remains orange ion, and every S nu remains a stationary set of you know the old omega 2, which is now omega 1. And f of g is still a gap, and that's because, well, suppose that you know g prime is a generic for this collapse of the v of g, and you take a real r in v in that model. Well, then that r is in v of the some initial segment of g given by some alpha less than omega 2. This forcing that added the gap was some iteration in length omega 2. So R together with G prime, right? But then you can see that by a density argument that R cannot split the gap. Okay, fine. So so finally, in this extension, there cannot be any ladder system on the new omega 1, which is the old omega 2, definable from these parameters, and simply because by homogeneity of the collapse, this ladder system, so this ladder system would be in V of G, which is impossible because that omega 2 that was the omega 2 of V of G. Okay, so right, and now if now kappa is inaccessible, and there's a such that and there's a kappa orange ion tree there, so I'll take any which is not weak compact. Then you take any partition of kappa into stationary sets, kappa many, and you take a generic for you know you take a kappa gap, you add it generically by CC forcing, and now the symmetric, and you look at the symmetric submodel of the extension of V of G by the collapse of omega, the Levy collapse turning kappa into omega 2. But, and this time generated by the names, which are fixed by automorphisms that fix some initial segment of this Levy collapse. And then it's standard that everything, the standard that this submodel will work. So in particular, there is no, so look, going to the last paragraph, there is no ladder system on omega 1 as such an object would be in V of G of H, and this for some generic H, for some initial, for the collapse of some alpha less than kappa, but that is impossible. Okay. Now let me give a related type of results that uses weakly compact cardinals. So suppose that there is a weakly compact cardinal, and then there's a partial order P such that, well, P forces that there's a partition of omega 1 into omega 1 many stationary sets, and then there's an omega 1 gap in the reals, but there is no orange ion tree which is definable from them. And also there's a symmetric submodel of a forcing extension of P which satisfies that there's a partition of omega 1 into omega 1 many stationary sets. There's a gap, but there is no orange ion tree. So again, the proof is quite natural. So kappa, you take a weakly compact kappa, and you take a partition of kappa into kappa many stationary sets. And you take now G a generic for adding a kappa kappa gap. And now you take M to be a transitive model of another set of C that contains in V of size kappa, contains V kappa, and then by the weak compactness, you take an elementary embedding from M into some transitive M with critical point kappa. And now this J can be extended to an elementary embedding from M of G to M of G of H, and this is so where H is a generic for the tail of this iteration that added the gap that starts from kappa. This is a countable support iteration. Now every kappa 3 T in M of G will acquire a kappa branch in this in N of G of H, right? Because it's it's a restriction. T is a restriction to kappa of J of T. So take any note of height kappa, but the tail of the iteration starting for adding the gap starting from kappa has a countable chain condition, and therefore T already had a branch, a kappa branch in N of G by the previous claim. So it follows that there are no kappa Armstrong entries after you force with this forcing. And now you argue, as in the previous theorem, that when you take, you take the forcing for adding the gap followed by the Levy collapse of kappa to become omega 1, that will work. And the weakly compact kernel is at least necessary to get the result, the independence result about over ZF. Okay. So now let me move on to considering partitions of omega 1 into stationary sets, which is another thing you can get from a lot of system. So it's easy to see that if you have so first of all, by the Solovey's construction, splitting of omega 1 into stationary sets from a lattice system, you can see that if just in ZF plus together with countable choice, you get that if C is a ladder system, then there's a partition of omega 1 into omega 1 many stationary sets definable from the ladder system. And also, if you have an omega 1 sequence of distinct reals, right? Again, over using countable choice, then there's a partition of omega 1 into countably many stationary sets definable from the sequence. Okay, so notice that here I just get countably many for the second one, but a partition into reals is something possibly weaker than another system. Now, a question I have at this point is whether ZF proves that if C is a ladder system, then can I define a stationary and co-stationary subset of omega 1 from C? How about this? Okay. So next, I want to mention this result. So fix a cardinal lambda, most omega, it's a non-zero cardinal. So I want to argue that, and this should be, yes, right. So that this right, so these two theories are equiconsistent, namely to have that ZFC plus is a measurable kernel on the one hand. On the other hand, ZFC plus there's a partition of omega 1 into lambda many stationary sets. But there is no partition of omega 1 into more than lambda many stationary sets definable from that partition. All right. So let me go through this. So let me prove that 1 implies 2. For this, let kappa be measurable. Then by a classical result of Cullen and Paris, we may assume that there are distinct, there are lambda many normal measures on kappa. So I can pick stationary sets of kappa consisting of inaccessible cardinals, lambda many of them, such that for all, for every index I star, I star is the unique I, such that as I star is in UI. Okay, now, so I have these lambda many different stationary sets, each one of them in a unique measure. Now I look at the Levy collapse of kappa to omega 1, and now I look at natural homogeneous forcing that is going to preserve the stationarity of all S1, and it's going to add a club C of kappa of omega 1, actually by countable initial segments, which is going to be contained in the SIs, and it's going to diagonalize all the UIs. So this forcing also adds an enumerating sequence length kappa of all these measures, and it's such that for every alpha in C intersection SI, alpha is in all xi beta for beta less than alpha. So yeah, so there's this natural forcing that adds this club by initial segments. And it's not hard to see that it preserves all the stationarity of all the SIs, and it's a homogeneous forcing. So now let H be generic for this iteration over V. Let C be the generic club that you added over the Levy collapse, and suppose it's a contradiction that there was a kernel lambda plus greater than lambda such that you have a partition into lambda, so lambda prime many stationary sets definable from the original one, which was in the ground model. Right? So now by homogeneity of this forcing, then this construction will be in V. So there must be some I prime, I star, such that you have two distinct indices, I0 and I1, such that A I0 intersection SI star and SI1 intersection SI star are both stationary in V of H. So, so exactly at most one of them can be at most one of these intersections can be in this UI star measure. So say that AI0 intersection SI star is not in the measure, but then this set is non-stationary since C was diagonalizing the measure. So that's a contradiction. And for the other direction, I'll just say that if you take, so you want to show that there's this partition of omega 1 into a small number of stationary sets, but there is no, there's no bigger partition into stationary sets definable from it. So for this, you take a set of ordinals A that defines this partition and codes and is definable from it. And then you look at HOD of A, so the HOD model constructed when you allow A as a parameter. And now you use a standard tree splitting argument, and you show that kappa is measurable in this ZFC model. Okay, so you proceed by contradiction, right? So you start from this from this partition, and then you eventually and you pick so you're constructing a tree of disjoint stationary sets, and at some point you end up with a stationary set such that the club filter restricted to it is going to be an ultra filter. Okay, so yeah, so let me maybe draw a picture here of what we've done. So just to remind you, right, of so we oops, how do I, okay. So we had, okay, so, yeah, okay, so let me draw. So we had this, ladder systems on top of everything else, and then we had unjoined trees, T, and then we had gaps. And of course, we have from gap, you can define an omega-1 sequence of reals. Okay. And then, of course, from this, you can define a sequence S of partition into stationary sets. And right, and then okay, and then also from this, you could define, you could look at partitions into countably many stationary sets. So this would sit on top of this, and essentially we've shown that you can separate pretty much all these things, right? And then you would have finite partitions below here. Okay. How do I go back to the slide? Okay. Yeah, the thing I wanted to erase this. Let me see. Okay, here's the eraser. Right. So let me now mention this. So we're still in the realm of partitions into small numbers into stationary sets of omega one, and I want to mention this. What's a very weak guessing principle in ZF that it's something that if you have that's actually intradefinable with a stationary and co-stationary set of omega one. So look at this principle that says you have a sequence X delta delta limit ordinal omega one, which X delta is a subset of delta, and now given any club C of omega one, you have this very weak guessing that there's, that there's at least some delta in C such that C intersection X delta is non-empty. And you also know that there's some delta in C such that C intersection delta is as non-empty intersection with the complement of X delta. Right. So of course, if you had say instead of C, you had a diamond sequence, then this will trivially have this property, right? So you look at any set, any set will be guessed somewhere, and also look at the complement of that set will be guessed somewhere. So yeah, so this is right. So okay, so now let's let me call by this the club filter on omega 1. And now I want to show that suppose you have ZF and that the club filter is normal. Then if you have, well, then this notion I just defined is intra-definable with a stationary and co-stationary set of omega 1. So for one thing, suppose that S is a stationary and co-stationary subset of omega 1, then there's a very weak guessing sequence definable over H omega 2 from S. And the second part is that suppose that X is a very weak guessing sequence, then there's a stationary and co-stationary set definable from it. Well, one is direction is easy, because if S is stationary and co-stationary, then simply look at the sequence of the intersections, of all intersections as intersection delta limit ordinal, and that will be a very weak guessing sequence. So this direction is trivial. And the other one requires a bit more of argument. So suppose that you have this sequence, which is a very weak guessing sequence, right? So remember, every X delta is a subset of delta, and if you have any club C, there will be a delta in C, which such that, so C intersection delta will intersect X delta, and there'll be another delta in C such that C intersection delta will intersect the complement of X delta. So now you have two possible cases. It could be the case, the first case is that in which for all alpha less than omega 2, either you have a club many deltas such that alpha is not in X delta, or you have club many deltas such that alpha is in X delta. Okay? So now for each alpha in omega 1, you let W alpha be the unique piece, that the unique set which is in the club filter. And now you look at the diagonal intersection of these W alphas, which is in the club filter by normality. And now you simply look at, now you observe that X delta 0 so the X delta is coming from this W, where delta comes from this W star, they cohere. So X delta 0 is the intersection which has delta 0 of X delta 1. And now you simply look at, you just union them up. You look at the union of all the X deltas. That's of course definable from this sequence, and it turns out it's a stationary and co-stationary subset of omega 1. So indeed, suppose that you are given a club C, and let's fix any club D that's contained in this W star. Now you take any delta, which is C intersection delta, and now you pick some, by definition of this W star, you pick some, right, so you pick some alpha, which is in C intersection D intersection X delta. But then alpha will be in S because delta was in this nice set W star, and alpha is in X delta and then W star. Okay. Okay. Right. And then the other case right, and then to show that also this club D has non-empty intersection with something in the complement, you use a symmetrical argument. Right. So the second case is the case in which there's some alpha with the property that both W0 alpha and W1 alpha are stationary. But then you take S to be just W0 alpha, where alpha is the first such that this set is stationary and co-stationary. And that's it. So that's all definable. Okay, so remember that I mentioned this result that if you have some lambda, which is a non-zero cardinal, it's at most omega, then These series are equiconsistent to have that Z of C and there's a measurable kernel, or Z of C and there's a partition of omega 1 into lambda stationary sets, but no partition of omega 1 into more than lambda stationary sets definable from that first partition. Now, I don't know how to convert the proof of these theorems, the theorem into a corresponding consistency result over ZF. That's not obvious. However, you can prove such results if you start with, say, a model of ZF together with determinacy. So, for example, by a classical result of Salovey, right, under the axiom of determinacy, the club filter on omega 1, which is delta 1, 1, is an ultra filter, and therefore you cannot split omega 1 into more than into two stationary sets. Now, the following theorem will generalize this. And before getting there, I want to remind you that if you take a non-zero n, then delta 1 n denotes the supremum of all the lengths of all the delta 1 n pre-will orders of the widths. And that's because I'm going to mention this. Sorry, where's the statement? For some reason, I don't find the statement in the theorem. So, right, sorry. So this theorem should say that, okay, if you, n, so the statement of the theorem should say that if n is a natural number and the axiom of determinacy holds, then well, delta 1, then in some forcing extension, delta 1, 2, so this kernel here, delta 1, 2, and plus 1, is omega 1, and there are exactly 2 to the n plus 1 minus 1 many stationary sets. There's a partition of omega 1 into these many stationary sets, but there's no partition of omega 1 into more than these many stationary sets. Okay, so you can have a model where you have exactly, you have a partition into, so when n is equal to 2, you have, say, 3 stationary sets, but there's no partition into 4 stationary sets, and so on. Okay, so the proof is like this. By a result of, so let lambda be delta 1, 2n plus 1. Then by a result of Kekri's, lambda is a successor kernel. Now for every infinite regular kernel mu less than lambda, you let C lambda mu be the filter generated by the mu closed unbounded subsets of lambda. And then by a result of Jackson, there are exactly 2 to the n plus 1 minus 1 many infinite regular kernels kappa below lambda, below this delta 1 to n plus 1. And lambda has a strong partition property, this property here. And this guarantees that lambda is measurable, and that moreover, the sequence of the set of the C lambda mu's is the sequence of filters is a set of is exactly the set of all normal measures on lambda. Okay, so you have exactly this 2 to the n plus 1 minus 1 many normal measures in lambda. Okay, so now let the kappa be the predecessor of lambda. And now you simply look at the collapse of kappa to omega, which is a finite tuples of ordinals. This can be well ordered in length kappa. So it follows that this collapse will force that omega 1 is lambda. And also in every club of lambda in the extension by this collapse will contain a club in V. But again, use the fact that the forcing can be well ordered. And hence the collapse will preserve the stationarity of all the sets of the Koff mu subsets of ordinals of lambda for the mu less than lambda. Okay, So now you take a name for a subset of right of some of these stationary sets for some mu, and take some condition in the collapse and suppose that and right and suppose that right you have this name for this stationary set, right, and know that p star p plus p bar forces that this stationary set is contained in the set as star of all the things that are forced to be in S dot by some condition extending p bar, obviously. Okay, so which is a stationary set in the universe. So by the fact that the collapse can be well ordered in length kappa, it follows that there will be a mu collapse D in V, which will be either disjoint from this S star, or will be contained in the the collection of mu such that of alphas in the set that P forces that alpha is in S dot, and this is for some uh, for some for some fixed condition P, extending P bar, right? Because we have a small number of such conditions. So from this, we immediately get that the collapse implies that there's no partition, right, into of kappa into more than these many stationary sets. Okay. Okay. So I have a question. I don't know if it's how hard this is to answer, but okay. Suppose that m is a natural number which is not of the form 2 to the n plus 1 minus 1 for any n. Is it consistent with ZF to have a partition of omega 1 into m stationary sets, but no partition of omega 1 into more than m stationary sets? That is my first question. And second question is the following. So by a theorem of Todorcevich, if you have bounded Martin's maximum, then you take a sequence of one-to-one enumeration of reals in length omega 1, then there's a well-ordered of H omega 2 definable from that sequence of reals. Another theorem of Justin Moore is that if you have BPFA and you have a ladder system C, which then there's a well-ordered of H omega 2 definable from that ladder system. Now, this the question is whether, of course, the ladder system is a priori more expressible than a sequence of reals. So the question is whether BPFA implies that if R is a one-to-one enumeration of reals, then there's a well order of at least the reals definable over H omega 2 from this parameter. So that is a question. Another question I have is that the following. So suppose that MM holds. Does it follow that being a subset of omega 1 not constructible from a real is strong enough to define everything else, right? The same situation that we had under star. So you could also ask, well, does it follow that if A is a subset of omega 1 not constructible from a real, and then B is another subset of omega 1, then there's a real R such that B is in L of R comma A. So this question, and another difficult question would be this one. So suppose you want to go higher up, and you want to have something like what you have in the star situation, but H omega 2 or something like that. So you could ask, could you possibly have large kernels, say X sharp exists for every subset of omega 1, and say that you have exactly 2 definability degrees over H omega 3 for definitions with parameters in the power set of omega 1. So the analogous thing that you got with star, right? That where you had exactly 2 definability degrees over H omega 2 for definitions with parameters in the reals, namely everything that's exemplified in L of R and everything which is not exemplified in L of R. Okay, so I think I'm running out of time, so that was my last slide, and yep. Thank you.
Okay, David, thank you very much. And any comments, questions?
Oh, I had a question.
Sure, yes, please go ahead.
Kind of, I mean, I think it was a really interesting talk, and but just kind of, I guess, going back to the beginning to that phi of AC.
Mm-hmm. Yes.
Is that about like just to like start to get an idea of like, is it about like what happens when you have two sets that are stationary and co-stationary, like and what does axiom of choice have to do with that definition?
Sorry, what is the axiom of?
The phi, I think it was phi of AC at the very beginning, towards the beginning.
Mm-hmm.
I just wanted to try to understand that.
Yeah, this here. Yeah.
Yeah. Is it saying something about like if two sets are stationary and co-stationary, then there's this kind of like relationship between them, or like, and what does the axiom of choice have to do with it?
Right. So say that you take, so now you take any T, right? This, you know, stationary, co-stationary, and now for, instead of S, you take any partition of omega 1 into omega 1, you know, stationary sets. And now, okay, now given any subset A of omega 1, you just look at the union of all these S alpha, such as alpha is in A, right? Just call it SA. Then this principle gives you some ordinal alpha, which codes this SA in this way, right? So you have this canonical function, so that everything on a club you are in T, you are in SA, even only if the order type, you know, the image of the function is in T in this switch device, right? So that gives you that you know, L of P omega 1 can see, right? Can see that this will order of H of P omega 1 from this parameter which is in it, right? So you look at the least ordinal for which you have a club coding your set in this way. Right? So the coding comes from looking at, as I said, so as your you know, your decoding parameter is this partition of omega 1 is S alpha less than omega 1 into stationary sets that you're using in the place of. So in place of S, S would be the union, this what I call SA, the union of S alpha, where alpha is in A. That would play the role of S. Yeah.
Okay, I think I understand a little more. Thank you. It's interesting.
Okay. Any other questions? Yes, Rahman, please. Oh, I see. So Rahman asked the question in the chat because he has a problem with the mic. So please look at the chat.
Okay. All right. So yes. So that gives you. I mentioned this, right? So he's asking, but is a higher version? Would this higher version imply within terms of most omega 3? And yes, because you have the same, right? I mean, you have the same, you know, well order in length omega 3 of actually of all of you know, H omega 3. So, yeah.
Okay, good. Any other questions? Okay, I think there are no more questions. So let's thank David again for his very nice talk. Thank you.